All right, here we go. All right, take a look at what I'm going to do is I'm not even sure why they have a chapter this short in the book. Matter of fact, to me, they could have combined with maybe another chapter, but they just made a real short chapter. And you did not get one of these last week, is that right? Okay. This is the first page is kind of like a summary of several things in the chapter, and then the second page is actually a practice quiz for the chapter 2. And again, there's not a whole lot in this chapter, so you'll see us go by there pretty quickly, and then we'll get into something different. Here's what I'd like to do. When you guys are doing your questions and things like that, without looking, just give me some words that don't look anywhere. Just say, I remember last week, I remember this word, I remember this diagram. Just tell me right now something that stayed with you even though nobody actually taught it to you. All right, ready? Let's go down the row. What's something you remember?
Homogeneous mixture.
Okay, homogeneous mixture. I say sometimes I say homogeneous. Distillation. Filtration. Wow, I'm impressed. Like nothing, all this, and you answered questions, you drew diagrams. You remember those two things? Okay, what else?
I guess like one of the diagrams that was like getting like salt water to like regular water.
Okay. And all right, and we're going to talk about that next.
Substance.
Substance. All right, the word substance in chemistry. Say it again.
Heterogeneous mixtures.
Homogeneous mixture and heterogeneous mixture, right? What about that? Physical change and chemical change. All right, next. Which one is it? About states of matter? Okay. Oh, that one, okay, all right. Actually, I wish he had used that as an example, but I understand it's a neat diagram. What do you remember? Compounds, okay? So, this chapter is really a lot about words, but it's about knowing the difference between one word and another. Like, what's the difference between an element and a compound? What's the difference between a homogeneous mixture and a heterogeneous mixture? And if you know these words really well, then we'll use those from now on for the rest of chemistry. Everything we do in chemistry, we'll use this. So, what we're going to start out with is, ooh, I have to be careful about that. Okay. Since you saw the diagram about states of matter, let's do something that they do even in elementary school, okay? But I hope I present this differently than they do in elementary school, okay? Elementary school, first of all, would say states of matter, whereas most of your higher level science books would call them phases of matter. So if I say, what phase are you in, you might say, well, I know there's solids, and there's liquids, and there are gases. Has anybody heard of another state of matter? I don't know if your book mentions it or not. Does anybody know of another state of matter? In all of your readings, do you guys ever read things besides Twitter? And just kidding. You guys you ever read things? Have you ever heard of another phase of matter? Have you ever heard of plasma? Is that what you're going to say? Oh, good. Even though we don't talk about plasma in chemistry class, it's more of a physics term, but plasma is a different kind of matter, but it's kind of like matter that's super energized to the point where it's almost like nothing's really together, like the atoms themselves are even apart. So I probably won't talk about plasma. Okay, now, here's what they would have done in elementary school. They would have done something like this. hey, what are the properties of a solid? And you say, well, solids, do they have a definite shape or not? Well, let's take a look at the solid. See this shape right here? Watch now, watch. Does it still have the same shape? So what do you think? Do solids have a definite shape? Okay, and in elementary school, you would have said yes. You would have been asked, in middle school they do the same thing. You would have asked to memorize the solids have a definite shape. Everybody got that? That's pretty easy. Let me ask you this. What about gases? What about gases? If I take a balloon and I squeeze it, does it have the same shape? What do you think? If I take the air in this room and hook it up to a compressor, could I take all the air in this room and put it in a scuba tank? So the air is taking up this space, this shape, and now it takes up this shape. So what do you think about gases? Do they have a definite shape? I keep looking at half your faces, and you're giving me clues about where we're going, okay? Okay, and I'd say, whether it's elementary or middle school, you would have been asked to memorize that. Now I'm going to skip this on purpose just for a minute. I'm going to skip this on purpose. The next question they would have had you memorize, not think about, they would just had you memorize it. Do solids have a definite volume? And volume is how much space you take up. And if you take a look at this rock, look how much space it takes up. What about now? What about now? What about now? What about now? Do solids have a definite volume? What do you think? Okay, write down what you think. What about gases? Well, not only did I take the air and put it in a scuba tank and change its shape, I also took a huge volume and turned it into a smaller volume, didn't I? So, can you see how there's definite differences between these two? But the question is, this is what they don't ask in elementary school, and this is what they don't ask in middle school, is can you draw, if you could visit a little tiny world and you could actually see the atoms that they're made of, what would you see? So I want you to draw me, what would you see if you could see the particles in a solid? And what would you see if you could draw the particles in a gas? And the reason I'm going to have you do that is, instead of just saying I memorize these two answers, I'm going to ask you why. Why did solids have a solid definite shape? Why do they have a definite volume? Why? All right, everybody got it? So I don't know if you use X's or O's or whatever you did, but whatever you used, I would say probably you were taught somewhere a long time ago that solids, the particles are really close to each other. Do you remember ever being taught that? Yes or no? Yes? Okay. How'd you draw a gas? Okay. I would say a lot of you would have been taught something like this. You might have even been taught this. What if you took some water and you heated it up and you turned the water from solid ice, you took ice and heated it and turned it into steam? You may have been taught by somebody that said if the particles had more energy, they would bump around and spread away from their next door neighbor and get so far apart they would change all the way to a gas. Have you heard that before? That's actually a fancy name. They're called the kinetic theory of matter, kinetic energy and energy of motion. And if this is really hot water and this is ice, this water is so hot it's steam that the kinetic theory says the particles are so far apart from each other. So here's my question to you. Instead of memorizing this, ask yourself why. Why does a solid have a definite shape, and why does it have a definite volume? And why don't you? And I want you to look at your picture. Now, I didn't do this, God did this, but when you get particles that are really close to each other, they tend to attract each other. And so the theory is, in a solid, the particles are so close to each other that they attract each other in every direction. And so if you try to change my shape, you can't. You can't. Because everybody's holding everybody in that shape right now because the particles are really, really close. And why is it that I can take a gas and change its shape greatly? Because look at all the space. How much attraction is there between this particle and this one? Almost zero. If I'm not attracting you, then what keeps us in the same shape? Nothing. And so, again, middle school might say, memorize that. I'm asking you to say, why? I want to do one more question here. Is the object compressible? Is it compressible? Now, does everybody know what that means? Compressible means that whatever volume you're taking up, I can make you take up less volume or more volume or less volume. If I compress you, it'd be less volume. So what do you think about solids? If I took a piece of metal like this one, if I took a piece of metal like that one, could I, in a really powerful machine, could I make it take up only that much space? Could I compress this much metal into this amount of space? He said, I don't know. Nobody's ever asked me that question. What do you think? I can compress this. But if I make it shorter, it's going to get wider. And it's still going to have the same what? A solid is still going to have the same volume even if I try to compress it. So can I compress it? No, I can't make it take up less space. I cannot. Now, I didn't do that. God did that where one kind of metal, you can put a lot of matter into a little space, and one of them you can't. Anybody happen to know that word? What's that word that starts with a D, and it means if you can put a lot of matter in a small space, you're very D. What's that word? If it takes a lot of space to put matter in, you're not very D. What is that word? Excellent. Dense. Density, like for example, both of these items right there, both these items, did you know that they actually have the same amount of matter in them? If I put this on a balance and put this on a balance, they both weigh the same. But this material, this lead is very dense, meaning I can pack a lot of matter into a very small space, and that's called density. And this is not very dense. This is aluminum. Same amount of matter. I can't make this amount of aluminum take up this amount of space. So density is kind of neat because God made us have things that are really, really dense on this planet, and some things are not. Okay, so now, what about gases? Can you compress gases? Absolutely. Matter of fact, we have, if you've ever gone to I-40 and you're going toward Winston-Salem, what's one of the most obvious things you see on the side of the road? They're huge and they're painted white. Have you ever seen those yet? And that's called the tank farm. And they're really wide. They're big cylinders, aren't they? Anybody know what's in those? Gas. Natural gas. Not gasoline. Gas. And gas can take up a huge amount of space. But what if somebody wants to buy some of that gas? What if I want to send it somewhere? What kind of a truck can I take? What kind of truck could go down the road with that much gas? It couldn't. So what they do is they take the gas and they compress it. And they cool it. Because when you cool it, it also gets close to each other like that. And they can actually change the gas into a liquid if they wanted to. And now you can get a truck that can take a huge amount of gas, but it's a refrigerated truck and a pressurized truck. See that? Now those are neat, but there is a danger. If you're a driver What do you think could happen if you have an accident? I would not want to be the driver of that truck if somehow that my whole tanker truck was full of compressed gas, all of a sudden broke a leak, or somebody had a bazooka and shot a hole in it. It would expand so quickly, it would tear out everything within about a quarter of a mile. Within a quarter of a mile, the compression would essentially kill everybody within a quarter of a mile. We do believe that the tanker trucks are the ones that carry gas. They are safe enough that we do allow them on the roads. But somebody had to make that decision, didn't they? Can we transport gas, a lot of gas, that way compressed, and not be a big danger to people? We have gasoline. That's a liquid, isn't it? We transport gasoline all over the place, don't we? That's dangerous, isn't it? All right, so now there's something that you should have noticed. What's something you noticed about the way I was lecturing today? I would say they would not do this in middle school. They definitely wouldn't do it in elementary. They wouldn't go solid, gas, skip the liquid. Solid, gas, skip the liquid. But I'm doing that on purpose because I want you to think about this, all right? I want you, before I write it down, I want you to write your answer for here, draw your picture, and answer that question, okay? Because right now you might be thinking, well, he's just teaching what they did in middle school. No, I'm trying to teach you completely differently. Go ahead, finish your notes, and let's see what happens. Liquids have a definite shape? Yes or no? Definite volume? Yes or no? What's the concept drawing of a liquid? And are they compressible? Yes or no? All right, is everybody committed yet? I'm gonna have you look at your neighbor's paper. So is everybody committed? All right, you guys look at each other's papers, and you look at each other's papers, look at each other's papers, and just look and see if they did exactly what you did. I don't think they're going to, but see if they did exactly what you did. Here, Julie, just turn around. Look, exactly. All right, did you learn anything? Did everybody match what you had? Is that what they had? Let's take a look. Let's go right here. Solids, liquids, gases, definite shape. Do liquids have a definite shape? So if I had a really tall container of water and I poured it into a bowl that was not the same shape, would it keep the same original shape? So no, it does not. Now, that tends to say, you know what? You must be maybe a little bit more like a gas than you are a solid. Next one. Do you have a definite volume? If I have 100 milliliters of water in a tall container and I pour it into the bathtub, how many milliliters of water is that now? It's still 100. Now, wait a minute. Definite volume, what does that mean? You must be kind of like a solid. Now here's where I'm losing you, okay? I don't want to lose you on this. You still think we're trying to just memorize a chart? That's not it. We're not memorizing a chart today. You told me why does it have a definite shape? Why does it have a definite volume? You told me because the particles are really, really close, didn't you? And then you said these don't have a definite shape and they don't have a definite volume because the particles are really, really far apart. And so here's my next question. Before we answer this one, I want you to answer this one. Can you compress liquids? Can you take, and I think if they could, wouldn't you have heard about it? You know, I don't have a lot of space in my house, so I'm going to buy a gallon of milk, but I want to buy compressed milk. And compressed milk only takes up half a gallon of space. It's a whole gallon of milk, but it's compressed. Have you heard that? Can you compress a liquid? And now, here's what I have to be careful, right? Okay? If you said that everybody you showed this to matched you, I'm very interested in what they do with their picture. Because here's humans. Let me tell you what's very, very human. I call this the Goldilocks principle, okay? Solid, the particles are really, really close. Gas, the particles are really, really far apart. What are humans going to do here? Papa Bear's porridge is too hot. Mama Bear's too cold. And what was this one? Just right. And you know what you want to do? I bet almost every one of you did it. I bet if these are really close and these are far, I bet you put these halfway. That's human. Humans do that. They do it all the time. I think they still teach it that way in elementary school. That's easy, isn't it? Close, far away, halfway. If the particles were halfway between these, wouldn't I be able to compress it halfway? You know why I can compress this? Because there's so much empty space. If there was any distance, I'd be able to compress it. If you drew it and it looked almost identical to a solid, then you did it right. But if you drew it halfway, you fell into that trap, and I know they still teach it that way in elementary school and maybe middle school. But I can tell you right now, these two bits of evidence right here tell me that there can't be hardly any space between the particles. Got that? So I would have drawn it pretty much just like the solid. Now, what is different? It seems to me the theory is that in liquids, there is a little space between layers. A little space between layers so that one layer might slide by the other layer. Got that? And so that allows liquids to be able to be poured. And that allows them to change their shape too. So this is the first thing I want to show you about states of matter. Now, another thing that you probably learned, and I was surprised, even my other two honors classes last week, they had trouble coming up with these words. Let's do this. What do you call it if you were to add, if you add heat to a solid, something's going to happen. It's going to change from a solid to a liquid. What's the word that you use? Go ahead and write it down. You write it down, and then you said, well, I might have to erase it. No, just go ahead. What do you call it when you add heat to a solid and it changes to a liquid? What's that called? Did you put melting? What did you put? What is it? Okay. Is that correct? Did we call it melting? What do you call the temperature at which this occurs? If I take ice at minus 10 degrees Celsius and I heat it, it'll become ice at minus 8, ice at minus 2. But when it becomes ice at 0 Celsius, something happens. I start seeing a little drop of liquid water. What do you call the temperature at which it changes from a solid to a liquid? I have the initials there. What is the temperature at which something changes from a solid to a liquid? What's it? It's two words. MP. Melting point. The melting point of water is 0 degrees Celsius. Isn't that right? Now, let's go here. Do you know that if I keep adding more heat, so we add heat, if I add more heat to a liquid, it will eventually change from a liquid to a gas. Okay, what word would you use for that? So you guys are in 10th grade, and you're kind of giving me this idea that you've never heard some of this stuff, or else you just think it's too easy or something. What is it?
Sorry, did he say 0 Celsius for the...
If it's water, see, there's all kinds of solids. Like this is a solid too, isn't it? But the melting point of this is not 0, so that's why I didn't write it in there. But melting point is the temperature at which it will change from a solid to a liquid. So what is the melting point of water, of ice? 0 degrees Celsius. Now something else happens for water at 100 degrees Celsius. What's this called? I'll give you the initials. BP. What is the temperature at which this occurs? What's that called? Boiling point. Yes? Okay. Now the boiling point of water happens to be 100 degrees Celsius, all right? But all the rest of them, you can look them up. You have to look them up. Now, so this is called boiling. But did you know that you could actually, some books, instead of using the word boiling, we like to use boiling for water, but a lot of people don't like to say that they boiled gold. If you change gold from a liquid to a gas, well, first of all, you better make sure if you change it to a gas that it doesn't get away from you. If you change it to gas and it goes out in the air, then you've lost a whole lot of gold. But people do this other word, which means the same. It's called vaporizing. Yes, no, you heard this word or not? Now, did you know that even water, if I put some water on this table right now, and I come back half an hour later, the water could be gone, couldn't it? But you know what? I never did get to the boiling point. The room never got to be 100 degrees Celsius, but all of a sudden, that liquid is gone. And you know where it went? It changed to a gas. What do you call that? What do you call that if you change to a gas and you're below the boiling point? What do you think? Kyle, you have an idea? What do you call it when water seems to disappear from the table and you say, well, it did what? Everybody get that? So all three of these words are similar in that when you change from a liquid to a gas, you can say, well, you boiled, you were vaporized, or you evaporated, right? Now, what's interesting is, did you know that we have some things on this planet that actually go like this? They go from a solid all the way to a gas, and you never see the liquid. There aren't a lot of those items, but there are some. I'll give you the most common I know of, right? Have you ever seen in your eyes, have you ever seen dry ice? Have you seen, you never seen it on TV, you've never seen it in person? Okay, you can actually go down here to Harris Teeter, and they sell it. They might not sell it to a teenager, I'm not sure, they might, but they would sell it to your parents. And it's actually not too bad. I think it's like $1 a pound. And so let's say you want 10 pounds, pay $10. But you want to make sure you have a container that you can take it home with. And dry ice is somewhere around, I'll use Fahrenheit today. It's about minus 110 degrees Fahrenheit. Now, if you let that dry ice sit on the table, you'll see a cloud develop around the dry ice. That's not the dry ice itself. What it is, the dry ice is so cold that it takes the water in the atmosphere and it turns the water in the atmosphere from a gas into a liquid, makes a cloud. And so when you put a piece of dry ice down, and you see sometimes Halloween where they put dry ice in water, you ever seen that? And bubbles come out. Bubbles are coming out, and it makes it look like witch's brew. And then you see this soup, this fog in the bowl. And what's that fog made of? A lot of people think it's from the dry ice, but it's not. The dry ice bubbles come up, and they're really cold. And when they burst, they make the top of the water cold, and the water that's in the atmosphere turns into a cloud. And so I've done that when I've had elementary kids in here before. I bought some dry ice, and we did it, where I had a bowl of dry ice and warm water. And then what I would do is I would take my mouth and go like this. I go. Now, what would happen is a cloud then would come out of my mouth. If you want to really be neat, you go like this. And make it come out of your nose. Now, you will not be hurt from that because even though there is something besides water, water is the cloud material. You see that? Does anybody know what dry ice is made of? There has to be at least one of you in here that knows that. Does one of you know what dry ice is made of? It's not made of water. Anybody? Before I read it? What's that? What is that? Carbon dioxide. If you were to freeze, if you were to freeze carbon dioxide gas, it would turn into a block that looks like ice, but it's not ice, because if you leave it on the table, you'll never see a pool of liquid. It'll just be gone. A lot of times when I do elementary kids, I'll get dry ice, I'll put it in a Ziploc bag, and I'll just go throw it on a table somewhere else, all right? Got a little Ziploc bag, I put it in there, make it tight, and I just throw it away, and I don't say anything about it. And about 5 minutes later, boom, like that. Because the dry ice changed to a gas, the gas built up pressure in the Ziploc bag, and it burst open like that. It makes a boom sound. If you were to, now be careful, I got careful what I say here. Don't do anything that you hear me say without your parents' permission. You get that? What if you were to take something like a Powerade bottle and you put dry ice in that and you closed it up? All right, the pressure would build up, build up, build up, and that pressure would get to be so great that if it did burst the container, it would sound like a gun going off. That's why you have to be careful. So you can get the police called on you if you were to make that big of a noise. And it's almost like an explosion. So anyway, when it's a gas, we just CO2, and you can't see CO2. Now, so when you put dry ice in water, you don't ever see CO2. It is true that when I do this, I am taking some CO2 in with the cloud. The clouds are made of water, but the CO2, I am taking some of that in there. I did one year where I took the CO2 and let it just turn into a gas, and then just put out a flame. It'll put out a flame. Okay, does anybody happen to know? I guess if you didn't know dry ice was made of CO2, then you wouldn't know this word anyway. This is called sublimation. Now, have you ever heard about something being sublime? Oh, that's sublime. If something sublimes, it actually changes from a solid to a gas. There's only one other material that you may run across like this in your lifetime, okay? My grandmother, I'm older than you, but maybe not your grandmother. But my grandmother, and certainly her mother, if you had sweaters made out of wool, if you had a pretty good amount of money, you would have had a cedar chest. And it would be something at the foot of your bed, and you would have all of your wool clothing in there, and it was made out of cedar. Now, cedar is a type of wood that gives off an odor that insects hate. They hate that odor. So if you put it in there, the moths are not going to go in there. They're not going to start to lay eggs and stuff like that. So you could protect them there. If you had a lot of money, you would have a cedar closet. You'd have a whole closet lined with cedar wood, and it would smell like cedar. Does everybody know what? You guys know anything about wood? See, okay, good. And insects hate that. But most people either didn't have a cedar chest or they didn't have that. So what do? Well, I could have a drawer in my chest of drawers, or you call it a dresser. And I could put my sweaters in there, and I could buy at the hardware store a really cheap material called mothballs. Have you ever heard of mothballs? See, I don't think your generation is even going to hear about them. Is that right? You might still be able to buy them. But when you buy them and open them up, you can actually smell them. If I took these mothballs and put them here, an hour later, the balls would be smaller. An hour later, smaller. An hour later, they might be gone. They change directly from a solid into a gas. And they give off this odor that insects hate. So if you were to keep them wrapped in like a sock or something, people used to use hoses, like women's hose, I don't know, they don't have, anyway. And you put them in there, put that in a drawer, that odor would be in that drawer, and the insects, the moths, would stay away. That's why they call them mothballs. There's only two materials that I know that you'll ever run across in your lifetime that undergo sublimation like that. Now, we need to do something else now. We need to go this way. You just reminded me that I'm probably going to move your seat, so thanks for reminding me of that, okay? What if you were to take something that was a gas and you took it and it's like steam? What if I took away heat? What would you call it if you go this way? What do you call it if you go from a gas and it changes into a liquid? Excellent. Were these people in the same class as you were last year and the year before that? Okay. Oh, okay, thanks. Just want to make sure. Okay, so we would say condensation occurred. A lot of you in the summertime, you'll have a glass that has maybe iced tea in it or something like that. And then you'll lay the glass down and then somebody will say, hey, put a coaster underneath that. Why? And they have these unusually common words. What's a common word for the water that drips off your glass on the outside? It's really condensation, but what do people like to call it? Hey, your glass is what? You ever hear anybody say your glass is sweating? Sweating? Ever heard that? No? What do you guys call it? Danny, what do you call it? Sometime in the summer, if somebody lays a glass down, it has iced tea or something like that, and they leave a ring of water there, where'd that water come from? It somehow leak out of your glass into the table? So, I never thought about that. What do they call it in your house? Leaking? What do they call it in your house? When you put a cold glass of iced tea or something down and it leaves a ring of water on it, what do they call it? Say it again?
Dripping or leaking.
Dripping? Okay, what do you think? Really? So nobody in this whole room calls it sweating? Really? What do you call it? Okay. Well, anyway, whatever your family calls it, you probably never thought about it, but really, honestly, did you think your glass actually was leaking? Was the glass slowly leaking and some of the iced tea actually got out of the glass? Well, that's what I thought. No, there's water right here. There's water right here. And what happens when cold glass comes in contact with this water vapor? Water vapor hits the cold glass and it makes it go closer and closer and closer, and it changes vaporized water into liquid water. And that's where that water comes from. It is condensing like that. Now, let's go this way. What would you call, whoops, dang it, I should have drawn that over here. That's my fault. What do you call it when you change from a liquid into a solid? This is the easy one. Julie, what do you think? At your house, do you have anything that's a liquid that you put it somewhere and it takes heat away, and when it takes heat away, it actually changes into a solid? All right? And so what do you call the process by which it went from a liquid into a solid? All right? Now, I don't know why, but a lot of students your age, they don't understand this. What is the freezing point of water? What is the freezing point of water? You say, what does that mean? What is the temperature at which liquid water changes to a solid? Anybody know? Everybody in this room should know. Every single one of you. 32 Fahrenheit, yes, or 0 degrees Celsius. What is the melting point of water? 0 degrees Celsius, 32 degrees Fahrenheit. It's the same temperature. If you add heat, we call it melting. If you take away heat, we call it freezing. But the temperature at which that occurs is the same. The boiling point is the same as the condensation point. And over here, I will tell you that not everybody likes to use the word freezing in science. They love using it for water. Hey, I just froze some water. Okay. Hey, I took some liquid gold and I froze it. A lot of people don't like to use the word freezing when they're talking about things like gold. So they call it this. Solidification. That's a fancy word, isn't it? It's solidified, isn't it? It's solidified. It turned into a solid. Okay, now, that's a lot for right now. I'm not done today, but this is part of the chapter. Part of the chapter has to do with states of matter, and I did go beyond. I went beyond what the book did. The only reason I don't like, and you like that diagram, it's a really neat looking diagram, I love it. The only reason I don't like it is because water is one of those things which acts a little different than anybody else on the planet. God's pretty neat. He has something that's all over the place. It's all over your body, all over the earth. Water is so unique, and yet it does something that most people don't do. If I took this aluminum and I heated it, the particles would get just a little bit further away, a little bit, and they start to melt, and they turn into liquid. If I heated it more, the particles would bounce around so much, they get so far away from each other, it would turn to vaporized aluminum. Vaporized. Now, most things go just like that. Solid, liquid, gas, gas, liquid, solid. Like that. Okay. Yes? Yeah, okay. Water is one of those things that's a little bit unique, and we'll talk a little bit more about water in another chapter. The only thing I don't like about that drawing is it should have shown the solid being the closest particles together, the liquid being very close, and the gas being far away. So it's a neat looking drawing, but it only looks that way because water is unique. All right, now, what was I going to say? Oh yeah, did you know that if you go to the gym and the lights are on, do you have any idea what's in those light bulbs that make them so bright? Has anybody ever run across this? The gym, the lights are so bright because we have a certain kind of a bulb that goes in there, and what's in there is vaporized mercury. Those are called mercury vapor lights. They've actually changed mercury into a gas and put it in that bulb, and so if you were to pop that bulb, it'd be kind of dangerous. So when they change it, and I've never asked them, but when they change those bulbs, they probably have to send them somewhere to be taken care of. Because if you pop the bulb, the mercury vapor will come out, which could be very harmful to you. If you were to breathe mercury vapor, that could be harmful to you. Any metal that's vaporized can kill you. You could vaporize copper. If you breathe it, you could die. Okay, so anyway, I want to tell you that because your normal street lights out here, they might be mercury vapor lights if they're really bright. If you know somewhere and the street lights are really, really bright, it's probably mercury vapor. Have you ever seen neighborhoods though where the street lights look kind of dingy? They're not bright white, they're kind of a yellowish white. They're kind of like, wow, you're not that bright. Have you ever seen that? There are whole states and whole counties that have passed laws saying that you can't have mercury vapor lights. Because what happens is you have so much light off that people can't appreciate the sky, the night sky. So in places like California, they probably don't let you have those kinds, so they give this other kind. If you've seen a street light that looks kind of dingy yellow, okay, those are called sodium vapor lights. And sodium vapor lights are not as bright as mercury vapor. Okay, now what I want you to do tonight, this is kind of like not real homework, but it's homework. I want you to look at this page and this page, and I want you to read it and highlight it. So when you come in tomorrow, every one of the words on these two pages, not tomorrow, I mean Wednesday, every one of the words on these two pages, just say, I understand those words. And what I'm going to do is try to show you how to classify matter. Okay, any quick questions? I should be able to grade all that stuff over here. I should be able to give it back to you. And please don't forget, I'm going to be here today after school. And I know that, I'm trying to think how many of you had some of you are going to have a grade change because I didn't have your old test. And so I will have to change that grade. All right, thank you.